Myself, Sanmol Sundaram, Professor, Sri Ramakrishna Engineering College. This video is about coupled circuits. This video covers self-inductance, mutual inductance, coefficient of coupling, drought rule, inductance in series and parallel coupled circuits. Then finally, writing KVL equation for coupled circuits. Let us see about self-inductance. So consider a single inductor with n number of turns. When current I flows through the coil, a magnetic flux phi is produced around it. So this is the circuit. I of t is flowing through this coil. This coil is having n turns. And phi is the flux produced by the coil due to the current flowing through this coil. According to Faraday's law, the voltage B induced in the coil is proportional to the number of turns and the rate of change of magnetic flux. That is, V is nothing but induced voltage will be equal to N into d phi by dt. But a change in flux phi is caused by a change in current. So therefore, we can write d phi by dt as, so you multiply and divide by di by dt and rearrange the terms. So you will get like this, d phi by di into di by dt. So now we will substitute this d phi by dt in equation 1. So you get v equal to n into d phi by di into di by dt. So also we know that v is equal to L into di by dt. So you compare these two equations, 3 and 4. Now this N into d phi by di, which is nothing but L. So L will be equal to N into d phi by 3. So that is what it is given in equation 5. L is equal to N into d phi by di increase. Unit of inductance is increase. So for a linear inductor, the above equation can be written as L equal to N phi by I. So that is, the phi by I is constant. So therefore, this N phi is called as total flux linking the coil due to the current I flowing through it. Therefore, the self-inductance is defined as the ratio of total flux linking the coil, that is N phi, to the current I which produced it when flowing through the coil. Its unit is Henry. Next we will see about mutual inductance. When two inductors or coils, they are in close proximity to each other, magnetic flux caused by current in one coil links with another coil, therefore producing the induced voltage. Mutual inductance is the ability of one inductor to induce voltage in the neighboring inductor. Let us consider the following two cases. Case 1. Two coils with self-inductance L1 and L2, that is, it is written here, which are in close proximity with each other as shown in figure. So they are placed close to each other. Coil 1 has N1 turns, this coil. Coil 2 has N2 turns. This coil has 2 turns. Now, coil is closely placed with this so that the flux link with this coil. Total flux is produced by this current, and the flux has two components. So this phi 1 is nothing but the flux that links only with this coil. Phi 1 2 is nothing but the flux that is linking with the neighboring coil. This flux is also produced by this current. So therefore, the magnetic flux phi 1 from coil 1 has got two components. Phi 1 links only coil 1, phi 1 2 links coil 2. Now the total flux phi 1 produced by first coil is phi 1 plus phi 1 So this summing of two fluxes gives phi 1. Thus, the flux linking coil 1 induces voltage in coil 1 and it is given by. So that is the voltage induced in coil 1 because of current I1. So the coil 1 has got N1 turns and this voltage is induced because of the flux phi 11. This is the flux linking the coil due to the current I1. So therefore you have to write N1 into T phi 11 by DI1. This should be multiplied with DI1 by dt because the voltage is induced because of the rate of change of current I1. So now this term is called as self-inductance L1. That is the flux, total flux linking the coil due to the current I1. That is called as L1 into di1 by dt. Similarly, voltage induced in coil 2 is called as V2. So now the voltage is induced because of the current flowing through the first coil, and because of the current flowing through the first coil, phi 12, that is some part of the flux will be linking the neighboring coil, that is called as phi 12. So therefore V2 is written as N2 into d phi 12. This is a flux produced by current I1 linking with the neighboring coil, that is coil 2. So d phi 12 by di1 multiply by di by dt. So this again can be written as, this is nothing but mutual inductance. So here the flux linkage is due to the current flowing in the neighboring coil. So M21 into di1 by dt. So what is M21? M21 is the mutual inductance between coils 1 and 2 due to current flowing through coil 1. Coming to the second case, same circuit but let current I2 flowing in coil 2. So now the current I2 is flowing through this coil 2, and because of this phi 2 is produced. So phi 2 has two components, phi 22 and phi 21. Phi 22 is nothing but the flux that is linking with this coil only, and phi 21 is the flux that is linking this neighboring coil, and this is also produced by the current I2, and hence phi 2 can be written as phi 21 plus phi 22. The voltage induced in coil 2 is P2 is, because of its own current, is given by N2 into number of turns into, and the flux linking this coil is phi 22 d522 by di2. This is because of current I2 into the rate of change of current is di2 by dt. So and this term, so that is the flux linkage is due to its own current. This is called as self-inductance of the coil L2 into di2 by dt. Similarly, voltage induced in coil 1 is, that is in the neighboring coil, due to this current S. So the flux linking this coil is phi 21, and due to the current I2 flowing in this circuit. So therefore V1 will be equal to, the number of turns in this coil is N1, and the flux linking this coil is phi 21. Therefore you have to write d phi 21 by di2 into rate of change of current is again di2 by dt, and this term is called as mutual inductance M12 into di2 by dt. So M12 is the mutual inductance between the coils 1 and 2 due to current flowing through coil 2. So if the two coils are same in both cases, then the mutual inductance also will be same. So therefore I can say that M21 will be equal to M12 equal to M. So in both cases the mutual inductance will be same. The mutual inductance M is measured in henries. So mutual inductance is defined as the ratio of total flux linking one coil to the current which produces it when flowing through the neighboring coil. Its unit is N2. Next, we will see about coefficient of coupling. It is defined as the ratio of linking flux to the total flux. Right. So K is given as, it is denoted by letter K. So for the first circuit, the flux linking with the neighboring coil is phi12 and the total flux produced by the coil is phi1. So this ratio is called as coefficient of coupling. Similarly, for the second case, the total flux, the flux linking the neighboring coil is phi21 and total flux produced by the coil is phi2. So the coefficient of coupling K will be greater than or equal to 0 and less than or equal to 1. It lies between 0 and 1. So now equation 8 and 11 can be written as, so that is the mutual inductance equations. So here instead of calling M21 and M12, just I am replacing them by M. So M will be equal to N2 into d phi 12 by di1, and another equation is M is equal to N1 into d phi 21 by di2. Now taking product of these two equations 13 and 14, we get M square equal to N1 into d phi 21 by di2 multiplied by N2 into d phi 12 by di1. So now you replace this phi 21 by k into phi2 into phi. Similarly, phi12 will be equal to k into phi1. So you replace phi12 by k into phi1. So you got this equation. Now, therefore, the equation can be written as m square equal to k square into n1 into d phi1 by di1 into n2 into d phi2 by di2. So if we see this term, this is nothing but the total flux linkage with coil 1 due to its own current. So this is nothing but self-inductance. So now you write this as L1 here. And this is N2 into d phi 2 by di2. Total flux linkage in coil 2 due to its own current. This is L2. So this equation can be written as m square equal to k square into L1 into L2. So this is written like this. Now from this equation for m becomes k into under root of L1 into L2 and the unit is inductance. So m is called as mutual inductance and it is in terms of coefficient of coupling and the inductance of the coils. So let Xm be the reactance of mutual inductance and this will be equal to k into, just you replace L1 by its reactance and we will call the reactance of the coil as X1 and reactance of coil 2 as X2. So you can write Xm as k into under root of X1 into X2 and unit will be ohms. Coefficient of coupling. It is the measure of magnetic coupling between the two coils. So the range is k is greater than or equal to 0 and less than or equal to 1. When k is equal to 0, this implies that two coils are not coupled. When there is no flux linkage between the two coils, then k will be 0. When k is equal to 1, it means the coils are perfectly coupled. The entire flux produced by one coil will be linking the neighboring coil. There won't be any flux leakage. When k is less than 0.5, this means two coils are loosely coupled. And when k is greater than 0.5, this means two coils are tightly coupled. So more flux will be linking with the neighboring coil. Now let us see about dot convention. Dot is placed at the terminals of coils to determine the polarity of the induced voltage in the mutual inductance. How to assign the dots to a pair of coupled coils? First, we have to place a dot at the terminal where the current enters one winding. So if there are two coils or two windings, first of all, you have to place a dot at which the current is entering into one of the terminals. Then determine the corresponding flux by application of right hand rule. Then apply right hand rule, determine the direction of flux. That is, if the fingers wrap around in the direction of assumed current direction, suppose this is the current direction and you have to hold your hand such that your fingers points to the current direction. In that case, the thumb will indicate the direction of flux. So this will be the direction of flux. The flux will be flowing. The current direction is like this, the current will be, that is the flux will be flowing in this direction. Then here you can see here, this is the core, the magnetic flux is shown here, phi 1, phi 2. So this is one winding, this is another winding. In the first winding, a current I1 is flowing. Because of phi 1 flowing in this winding, using right hand rule, you can determine the flux direction. Suppose this is the flux direction phi 1. Now, flux in another winding will oppose the first flux. So you have to remember that the flux in this winding always it will oppose this flux. So the current direction will be such that the flux will be flowing in the opposite direction to that of the main flux phi 1. So now again use the right hand rule to find out the natural current direction corresponding to this second flux. So now we know the flux direction, you can determine the current in this winding. For example, this is the current direction. So the current leaves from this terminal, the second winding, to produce flux in this direction. Now place the dot at the terminal of the second winding where the current leaves the winding. So now already we have placed a dot where current is entering the winding, one of the winding. In another winding, you have to find out the natural current direction, the terminal at which current leaves the winding, that is this point. So now you have to place the dot. So now further this can be drawn like this. So every time it is not possible to draw the core, right? Only the two coils will be drawn and a dot will be placed at the terminals. So this indicates that when the current enters into this terminal in this winding, in another winding the current will be leaving at this terminal. Or also vice versa also is true. Current is entering in this terminal, the current will be leaving in this winding. Okay. So now the polarity of the voltages in self-inductance and mutual inductance. Let us consider these two cases. In these two cases, the current is entering in one winding at one dotted terminal and current is leaving at another dotted terminal. You can see here I1 is entering the dot, I2 is leaving the dot. In the other case, that is, it is reversed. So I2 is entering the dot, I1 is leaving the dot. So if this is the case, the polarities of mutual inductance voltage and self-inductance voltage will be opposite. So if the inductance has a positive sign, mutual inductance voltage will be having 97. The second case, you can see that the two dots are placed here. If both the currents are entering into the dot terminal or both the currents are leaving from the dotted terminal, then we have to use same sign for mutual inductance voltage and self inductance voltage. So that is also stated here. 1. When the assumed currents both enter or both leave a pair of coupled coils at the dotted terminals, the sign on M terms will be same as that of sign on M terms. Let's say here, so they are mutually coupled. In both windings, the current is entering. I1 of t is entering this dotted terminal, I2 of t also entering the terminal. So in this case, the mutual inductance voltage will be M into di1 by dt. The second point. Suppose we are passing current I1, so induced voltage we get it at the second winding. If it is reverse, that is, you are going to supply current in this winding, and you are going to get mutual inductance voltage here this side. In this case also, this will be positive. This V1 will be equal to M into di2 by dt. So that is, this mutual inductance is because of the current flowing in this winding segment. Second case, if one current enters at the dotted terminal, one current is entering, and while the other leaves the dotted terminal, other is leaving, the sign on M terms will be opposite to that of the signs on the N terms. So if one it is entering and another it is leaving, in that case sign will be opposite. The mutual inductance voltage will be having a minus M into di1 by dt. Whereas in this case it will be minus M into di2 by dt. Coming to the dot convention for coils in series. Let us find out the equivalent inductance of coupled coils. So here we have two inductances and the dots are shown in the inductance. They are connected in series, and M is the mutual inductance between the coils. They are placed close to each other. I is the current flowing in this path. So now the equivalent inductance this will be equal to L1 plus L2, and here you have to either add or subtract this mutual inductance. So in this case you have to add, right? If the current is entering into the dotted terminal in both the coils, or current is leaving at the dotted terminal in both the coils, you have to use positive sign. You have to add this 2M. 1M for this coil, another M for this coil, the 2M. So this is called a series aiding connection. So the inductance value is L1 plus L2 plus 2M. 2M gets added to this. Next, another case. Here, current is entering into the dotted terminal here, whereas current is leaving from the dotted terminal. If a case arises like this, then the equivalent inductance will be L1 plus L2. You have to use minus sign, minus of 2M. This is called a series opposing connection. Now let us write an equivalent inductance equation for this case. So here there are three coils. These two coils are mutually coupled, and likewise 2 and 3 are mutually coupled, likewise 3 and 1 are mutually coupled. So there are mutual inductances here. M1 is the mutual inductance between 1 and 2, M2 between 2 and 3, and M3 is between 3 and 1. Current I is flowing. So here current is entering the dotted terminal. In this case also current is entering into the dotted terminal. In this case also current is entering into the dotted terminal. So therefore L equivalent will be equal to L1 plus L2 plus L3, since M1 is the mutual inductance between these two coils. Since in both cases current is entering into the dotted terminal, you have to put plus 2. Similarly, for second coil and third coil also, the current is entering into the dotted terminal. So therefore you have tried 2M2. Then between 3 and 1 also the current is entering into the dotted terminal. So you have tried 2M2. This is the equation for equivalent inductance. To get equation for reactance, so you replace the inductance value by reactance, that is x1 plus x2 plus x3, and for this you write the reactance of mutual inductance, that will be plus 2xm1 plus 2xm2 plus 2xm3. xm3 is nothing but the reactance of m3. So another example slightly different from this. In this case, current I is entering into the dotted terminal, the first coil, whereas in the second and third coil current is leaving from the dotted terminal. So now let us write the equation. L equivalent will be equal to L1 plus L2 plus L3. Then we have to determine the polarity of the mutual inductance voltages or mutual inductance. That is, M1 is the mutual inductance between coil 1 and 2. But you see the current in this case is entering dotted terminal, in this case it is leaving the dotted terminal. So therefore, since in one inductor, one coil it is entering and in another coil it is leaving, so you have to write it as minus 2M1. Coming to M2, you see here in coil L2 current is leaving out from the dotted terminal and L3 also current is leaving from the dotted terminal. Therefore, you have to write plus 2M2. Then between coil L3 and L1, you will find that again this current is leaving from the dotted terminal and here current is entering. Again you have to write 2M3. Similarly, the equivalent reactance will be equal to reactance of this L1 is x1 plus reactance of this is L2 is x2, reactance of L3 is x3, minus of 2 into reactance of M1 is xm1, M2 is xm2. You have to write plus 2 xm2 plus this one as 2 xm3. So this is the equation for equivalent reactance. Then let us compute the equivalent impedance of the series coupled circuit shown in figure below. You consider this case, L1, L2, L3 are given. So here current I is flowing in this path. So current is entering into dotted terminal. Here current is leaving from the dotted terminal second coil, whereas third coil current it is entering. Their mutual inductance are shown in figure. So L equivalent will be equal to, first is sum of all the inductance L1 plus L2 plus L3. So to determine this, the polarity of the mutual inductance, so M1, that is between coil L1 and L2, the current is entering here and current is leaving from the terminal. Therefore, write minus 2 M1. Similarly, for this M2, you consider coils L2 and L3. Current is leaving from coil 2 and current is entering from the. Again, you have to write minus 2 M2. But whereas coil L3 and L1, you can see that in both the coils, current is entering at the dotted terminal. If current is entering at the dotted terminal in both coils, or current is leaving the dotted terminal in both the coils, then you have to write plus. So plus 2M3. So substitute the values, this will be equal to 7M2. Suppose if the reactance of this inductance L1, L2, L3 and the reactance of mutual inductance M1, M2, M3 are given, then you can use this formula XQE, S equivalent equal to X equivalent equal to X1 plus X2 plus X3, and for this it is minus 2 XM1, and for this this is minus 2 XM2, and for this is 2 XM3. So substitute all the reactance values, you get the values. So the values in volts. Coming to two coupled coils in parallel. Suppose the coils are in parallel. How to get the equivalent inductance? So now consider this case. V is the voltage source and I is the current supplied by the voltage source, and this current it gets divided. So in this branch it is I1, in this branch it is I2. These are the two coils, they are coupled, and they are placed close to each other, and there is mutual inductance, and the dots are also shown here. So for the given current directions, now let us write the voltage equation. So the voltage across this inductor will be equal to the self-inductance voltage plus mutual inductance voltage. That is, self-inductance voltage is Jx1 into I1. Look at Jx1 into I1. That is, and the mutual inductance voltage in this inductor due to the current I2 will be plus Jxm and Xm into I2. So why we are writing plus here? Because current in both the coils, they are entering into the dotted terminal. So you have to write here plus. Similarly, also you can write voltage across this coil. Since both coils are connected in parallel, so the voltage across this coil also will be same as that voltage across this coil. So we'll write an expression for V. So V will be equal to, so the mutual inductance component will be, that is, the mutual inductance voltage will be because of the current in this hybrid coil. Therefore you have to write Jxm is the reactance into I1 plus, and voltage in this inductance, that is Jx2 into I2. So these are the two equations. Now what you do is, from these two equations you get X equivalent as V by V. So when you try to get an equation for this ratio of V by I, this will be equal to J into x1 x2 minus xm square divided by x1 plus x2 minus 2xm. So x1 is the reactance of inductance L1, x2 is the reactance of inductance L2, that is second coil inductance, xm is the mutual inductance reactance. And from this we can write an equation for L equivalent. You know that x1 is nothing but omega L1 and x2 is nothing but omega L2 and xm is omega n. So substitute and get an equation for L equivalent will be equal to L1 plus L2 minus m square by L1 plus L2 minus 2m. This is equation. Similarly, we take this case, current is entering at one dotted terminal in this coil, whereas this current it is leaving from the dotted terminal. In this case, the equation will be slightly different. Only the mutual inductance component will be having a negative sign. So here both signs are positive, here both are negative. Why? Because current enters into dotted terminal on coil and current leaves from the dotted terminal on coil. So that is the only change. Then again you obtain the ratio V by I. This will be equal to L equivalent will be equal to L1 plus L1 into L2 minus m square divided by L1 plus L2 plus 2m. The only difference is here you have plus sign, whereas you have minus sign here. Now we will see a few coupled coils and we shall see how to write the KVL equations. So now you take this circuit, there are two meshes. So Vs R1, J omega L1, J omega L2. These two are coupled coils and the dots are shown here and the mutual inductance is shown here. Mutual inductance, M is the mutual inductance between the two coils. And R2 is common between S1 and S2, R3 is here. So now for mesh 1 we'll write the equation as usual. We'll directly write the equation. So the I1, so this part is, you have to sum up all the resistance and reactance in this mesh and write that will be the coefficient of I1, that is R1 plus J omega L1 plus R2. So this is into I1. for mesh 1 to write this I2 component. So you have to see which is the element common between first mesh and second mesh. It is R2. R2 is common between mesh 1 and mesh 2. So now you compare the current directions. I1 is flowing from top to bottom, whereas I2 is flowing from bottom to top. So they are opposite. Therefore, you write minus sign into the voltage across this will be R2 into I2. Then coming to the mutual inductance. So in the first mesh, this inductance is present, whereas this inductance is mutually coupled to this inductance. Because of this current, there will be some mutual inductance, and as a result, there will be voltage across this mutual inductance. So that component we have to write it like this here. So actually, the magnitude will be j omega m into this current. This one current only, because of this current only we get this voltage term. So j omega m into I2. What about the polarity? So when you write this polarity, when you see the current direction entering into the dotted terminals. In this case, I was entering into the dotted terminal, whereas here I2 is leaving from the dotted, right? Use here minus sign, and this will be equal to Vs. Normally we used to write minus Vs equal to 0, and now if you write this Vs in the right hand side, you can write it as plus Vs. The second mesh, coming to second mesh, again while writing second mesh, to want to write the coefficient of I1, you find out which resistance, which component is common between mesh 2 and mesh 1. It is R2. So now what you have to do, check the current directions. So these two directions, I1 and I2. I1 is going top to bottom, and I2 is going from bottom to top. So therefore the current direction opposite. So you have to write here minus sign. Therefore you have to write I1 into R2 here. Then plus for I2, the second mesh, you have to sum up all the resistance and reactances, and you have to write it here. R2 plus R3 plus j omega L2 into I2. So this is for this second mesh. Then coming to the mutual inductance, this coil is coupled to this coil. Therefore, there will be mutual inductance because of this current. Because of this current, there will be voltage in the mutual inductance. So the value will be minus j omega m into I1. Minus j omega m into I1. So why minus sign? This minus sign, because if the current enters in one dotted terminal, the current leaves from the dotted terminal of another coil. In that case, you have to write minus sign. So minus of j omega m I1 equal to 0. These are the two equations. So if the values are given, you have to substitute the values in these two equations and solve the equations. The example 2. Now let us write the equation for the circuit. So this circuit has a voltage source Vs, resistance R1, and two coils L1 and L2. So they are coupled, and mutual inductance is M, and in this mesh we have R2 and j omega C, these two elements, and current directions. I1 is the first mesh current, and I2 is the second mesh current. I will write equation for the first mesh. So here for I1, the coefficient will be to add all the resistance and reactance in this mesh R1 plus j omega L1 plus j omega L2. This multiplied by I1. This is the I1 component plus an I2 component. So while writing equation for mesh 1, you have to find out which component is common between first mesh and second mesh. It is j omega L2. So you write j omega L2 into I2. for this, and the polarity, this plus or minus sign, how you should find is if the current directions are opposite. For example, in this case, I1 is flowing from top to bottom, I2 is flowing from bottom to top. So they are in opposite directions. So write here minus sign. Then you have to write the mutual inductance voltage. First we will write mutual inductance voltage for this coil. So here the mutual inductance is voltage because of the current flowing in this coil. What is the current flowing in this coil? For when writing equation for first mesh, so current in this will be I1 minus I2. So therefore, the mutual inductance voltage in this coil will be J omega M into this current. The coil which is coupled to is I1 minus I2. So what about this sign? The sign will be here in this case it is plus. So how to find the sign? When the currents are entering into the dotted terminal in both the coils, the current is leaving at the dotted terminal in both the coils, you write here plus. In one coil if it is entering, in another coil it is leaving, you write minus. So in this case I1 is entering here, and in this case the current we have written it as I1 minus I2 as the current in this inductance. Therefore this current, since I1 we have considered as positive, this current is also entering into the dotted terminal. So therefore we have to write here plus J omega into I1 minus I2. Then coming to this, so here this again this is coupled to this mutual inductance is M. So the mutual inductance voltage will be because of the current flowing in this coil. It is J omega M into current I1. So you have to write this is equal to Vs. Normally we used to write minus V equal to 0. So if you directly write Vs on the right hand side, so the sign will be positive. Coming to the second equation for mesh 2. So for while writing equation for mesh 2, so the component I1, right, this will be find out the element common between first mesh and second mesh, that is J omega L2. So this into I1 is this component. The minus sign is because these two currents are flowing in the opposite direction. Next I2 components, I2 to sum up all the resistance and reactance in this, that is R2 minus J omega C plus J omega L2, and so this will be the coefficient of I2. And coming to the mutual inductance, only this inductance is present here, and the mutual inductance voltage will be J omega M. And what is the current? So which coil is coupled to this? This coil. So what is the current flowing in this? It is I1. So J omega M into I1. So what is the sign? So here minus sign is because you can see here while writing equation for second mesh, this current is entering into the dot terminal, whereas here I2 is the second mesh current. This current is leaving from the dotted terminal. So therefore you have to use minus sign here. So minus J omega M I1 equal to 0. This is how you should write the equations. If the values are given, you can substitute and solve these equations, find the currents. Another example, let us consider this cycle. So R1 is there, J omega L1, this is one coil. Here there is another coil, J omega L2, and here resistance. I1, I2 are the currents and the meshes. M is the mutual inductance. Now let us write equation for first mesh. So the component I1 component will be, you have to sum up all the resistance and reactance, that is R1 plus J omega L1 is associated with I1, and with I2 first mesh equation. So you have to find out the component which is common between first mesh and second mesh. It is J omega L1 into I2 here, right? And the sign depends on the current directions. So I1 is going from top to bottom, I2 is going from bottom to top. So you write minus sign here because current directions are opposite. Then coming to the mutual inductance voltage. Mutual inductance voltage in this coil will be j omega m into what is the current? So which coil is coupled? This coil is coupled. What is the current in this? It is I2. So j omega m into I2. This will be equal to Vs. This is first equation. Coming to the second equation. So I1 component is, that is your, this component is common between first mesh and mesh. So therefore you have to write j omega L1 into I1. So here minus sign you are right because the current directions are opposite. Plus, while writing I2, you have to sum up all the resistance and reactance in this mesh. That is R2 plus j omega L1 plus j omega L2. Then coming to the mutual inductance, there are two inductances are present. So you have to write the equations. So first, we will write for this. So for this is what is the current flowing in this? It is I2. So therefore, mutual inductance voltage for this coil is j omega m into this current. This coil is coupled with this, so into. So minus sign or plus sign you have to decide. So here, while writing equation for second mesh, you have to consider the current I2. So I2 is leaving from the dotted terminal, but whereas it is entering here. So in one coil it is leaving, another coil is entering. So therefore, you write here minus j omega. So coming to this inductor in this coil. So the mutual inductance voltage will be j omega m into the current in this. Current in this is I2 minus I1. While writing equation for second mesh, you have to write I1 minus I2. So why I1 minus I2? Because they are in opposite direction. So j omega m I2 minus I1. So what about this sign? It's minus because this current, one current is leaving from the dotted terminal. In another coil, this current is entering. So you have to write here as minus sign. These are the two equations. So to solve these two equations. Coming to another example. So here let us write equation for first mesh and second mesh. So here there are two coils. They are present in the second mesh itself. So since both coils are coupled and the current flowing through these coils is also I2. So writing equation for first mesh, there is no mutual inductance in this. Therefore, the equation will be for I1 it will be R1 plus minus JHC plus R2 to I1, and for I2 you have to find out which component is common between first mesh and which is I2. So you have to write I2 into R2. So here I placed minus n because these two currents are in opposite direction. So this should be equal to Vs. Second equation. So for I1, again this is element is common between two meshes. You have to write I1 into R2 and the minus sign because these two currents are opposite. Then for I2, you have to sum up all the resistance reactance in this mesh, R2 plus j omega L1 plus j omega L2. Then coming to the mutual inductance. So for this inductance, so this coil is coupled here. So you have to write j omega m into I2. Again for this it will be j omega m into I2 because in both coils it is it. So you are getting right. Now you see the chain. So in this coil the I2 is entering, whereas in this coil it is leaving. So in one coil it is entering, another coil is leaving. Therefore you have to write for this mutual inductor also will be having a negative sign. For this also it will be a negative sign. Therefore you have to write, if you add them you will get minus 2 j omega m I2. So this equated to 0. This is the equation for the second mesh. So you have to solve these two equations, find the unknowns. So usually unknowns will be the current, find the currents if the other values are given. And coming to this one, here there are three coils, they are coupled. So M1 is mutual inductance 1 and third coil, and M2 between 2 and 3, and M3 is between L1 to 2. Now let us write the equations. So for mesh 1, the equation will be, for I1 component, it is let us sum up all the resistance and reactances R1 plus j omega L1 plus j omega L3 plus R2 into I1. Then coming to I2, so this branch is common, but it must be sensitiveness, and current directions are opposite. So therefore you write minus of R2 plus j omega L3 into I2. Then coming to the mutual inductance, first let us write an equation for this. The equation for mutual inductance voltage is here. Here you have to write the voltage drop across mutual inductance uh, due to M1 and M3, because these two coils are coupled to this coil. So for this it will be, what is the current flowing in this? It is I1 minus I2 while writing equation first. So I1 minus I2 is the current. So j omega M1, sorry, j omega M1 into I1 minus I2 is the mutual inductance voltage due to this M1. What about sign? If you see the sign, so here I1 is entering here I1 is leaving. Therefore, you have to write minus sign. Then coming to this coil, coming to this coil, the mutual inductance is again M1. So you have to write J omega M1 into, what is the current in this coil? It is I1. So you have to write J omega M1 into I1. Then coming to this, here there is one mutual inductance. So for this it will be J omega M2, J omega M2 into I2, because this mutual inductance is because of this current in this coil, this I2. I2, this will be equal to Vs. So you have to write here. So there will be so while writing for this loop, so here mutual inductance voltage due to M1 and due to M3, and similarly for this due to M1 and due to M2. So there will be four components of mutual inductance voltage. Similarly, while writing for second mesh, so for I1 you have to write as R2 plus j omega L3 with minus sign you have to write. For I2 you have to sum up all the resistance and reactance in this second mesh, R2 plus j omega L3 plus j omega L2 minus j omega C. Then mutual inductance voltage. So coming to this one, the M1, M1 is the mutual inductance between the coils. So therefore we can write it as j omega M1 into, what is the current in this? It is I1, j omega M into I1. So now this sign, because here it is used positive sign, because here current I1 is entering the positive terminal. Here, while writing equation for second mesh, the current I1, I2 is also entering the dotted terminal. Therefore, so you have to write plus j omega M1 into I1. So coming to this M2, so M2, so you have to write as j omega M2 into, right, these two are coupled. What is the current flowing in this? It is I2, j omega M2 into I2. That will be the mutual inductance voltage. What about the polarity? So you're writing equation for second loop, you have to consider the current I2. So I2 is entering here, whereas it is leaving here. So therefore you have to use minus sign, this point. Then coming to this coil is again M3 chem is the mutual inductance. Therefore we can write this J omega M3 into what is the current in this? It is I1, J omega M3 into I1. Rho plus and sign. So the current in this I2 is leaving the terminal, whereas current I1 is entering the terminal. So they are in one coil it is entering, another coil it is leaving. Therefore, you have to write it as minus j omega M3 into I1. Then coming to this last term, that is this coil is coupled to this coil. What is the current in this coil? It is I2 minus I1 when you are writing for seconds. Therefore, j omega m2 into I2 minus I1 is the voltage. And what about the sign? See here, I2 minus I1. So I2 direction is like this. It's entering. So current is entering here, dotted terminal. Whereas here, I2 is leaving the dotted terminal. Therefore, you have to write minus sign here. So anyway, thank you. I hope you have learned about self-inductance, mutual inductance, coefficient of coupling, dot convention, and how to write equations for coupled circuits. Thank you.